because I've been motivating you guys that this is one of the slow components, right? Imagine like when you have data access, it becomes like a step function where if you have your data in the register, it's really quick, right? It's almost instant. You can get the data right away. And that's awesome. Then when you have to go to the cache, that is slower. L1 cache, if you read CPU specs, usually it's time around 4 to 5 cycles. Not bad at all, right? Then the L2 get worse, like 10 to 11 cycles. Then DRAM, when you look at that, it's like 50 to 100 cycles. 50, you were lucky. 100 something, if you're not so lucky. We talk why is that range today, all right? Then, if you miss in DRAM, what happened? What happened? You have like 1,000 Chrome tabs. You either choose to reboot your computer, close Chrome, and free up the memory, right? Because you cannot afford to have a lot of paging. You don't want to go to the disk many times. Now, we kind of ended the lecture on Tuesday with out of order. I told you we are not going to test you on out of order, all right? But it's kind of like something that we have to talk about when you think about the memory, because there'll be some question that pops up in your mind. You think about in order pipeline, why is this happening? But with out of order, this thing will happen, okay? So out of order with the memory means that I keep going, trying to execute whatever instruction is ahead of me, which means that, let me put it this way. Let's say this is my instruction stream, this is load to A. Out of order means that I'll keep going, right? I don't stop at load to A and stop my pipeline. I'll keep executing. And then I have another load, right, to address B. And then I keep going because I can keep reading future instruction, right? Quick question, if you're wondering how far can you read, usually that's the buffer size for how many instructions can you read ahead of time, which is these days like 256, which is a lot, all right? So keep going down. You have another load to see, right? What does that mean? It means that CPU issue how many memory requests? 3 at the same time, right? This is kind of awesome, right? Instead of paying for the price of 1 memory access, I can basically execute 3 almost at the same time. And hopefully DRAM handle that, okay? There are also this dependency kind of thing, which is quite important. Let's say I have load to A, and that address is being loaded into a register. What does it mean? It means that anyone who needs that register has to be what? Has to wait until I have A available, right? So that becomes one of the critical parts of your program. You want to make sure that you service these guys quickly, because if I have a load to B and then if no one needs B, it's that sad guy that no one needs. I mean, I don't care. I can delay them as much as until the next instruction really need that guy. All right. Now, how to treat the load instruction? One thing is when you have a load, obviously, if you have previous store to DRAM that you trying to update DRAM with, right? Maybe I can check the previous store and say, hey, is that my address? If you have my data, I know it's not in DRAM yet, give it to me. Because it's the same address, right? Let's say you have instruction run like this, right? I have store to A, and then later I have load to A. Do I have to go to DRAM for the load to A? Not really. I can forward, right? Forward the data add that address by the store to the load. Another thing about store, does store block the pipeline? Will there be anyone depending on the store for the compute instruction? No, right? Only the load depend on the store, and load cause dependency, but store doesn't really cause dependency, right? If I have ongoing store and if that's dependent load, I can always forward them, which means the store is not the critical part. It's not a part of my bottleneck, right? That's one thing you might see in modern DRAM. They'll kind of deal with writes differently than read, because write doesn't block your progress. Now, You might also look into software programming and other things, right? You might learn about writes are bad. For example, parallel program. You want to limit number of writes or concurrent writes. That's for a different reason, because you need to have only one guy modifying your data. This is different. This is basically inside a pipeline. I can always forward the data I'm storing to the future load. Okay. So the obvious part, which is what I just said, if I have a load instruction, I basically can check the queue that would maintain all this previous store requests and say, hey, anyone try to update this address? If you have the data, please forward it to me. That's it, right? The not so obvious part is that if I have something that looks like this, I have store to A, and I have a load to A. But it just happened that I execute this first, followed by this guy. Because we are doing out of order, that store might be depending on some other instruction that blocks me, right? Then when I have the store, I can also forward A to the whatever load is depending on my address. Again, the same logic. If I have a previous store in the buffer, I can always forward, okay? And you can also have, I told you these are the queue, right? So we can always combine the two queues. Now let's actually now show how the design diagram looks like, okay? Again, we are trying to do multiple load, multiple store at the same time. And what I said right now is store, as I said, doesn't block the pipeline. I can always forward the value I'm trying to store to the future load. All right. The load, that's the one that blocks your pipeline. So in CPU design, reading the data is really important. You want to be able to service them really quickly. Writing the data, that's another myriad of problems that has to do with coherency and consistency. Can everyone see this updated version of my data when I write to it? But that's a totally different problem that we are not going to talk about today. Okay. Now, let's say you have a load that comes after the store, right? Now, to have that buffer, what do you need? Basically, when you go to update DRAM, it will take some time, so it makes sense to buffer them. The data that you need are, what's the address I'm trying to load to? What's the data? And is that a load or is that a store? All right. So now you would allow your CPU to run out of order. And then if you have future instruction that need the data from this guy, forward it. So here's an example. Let's say I have a load buffer and store buffer. Initially, I have a load to A. Then I have a load to B. Then I have a load to A again, right? The first question you might have is, do I issue one request to DRAM or two requests? Would it be okay to just handle the first load and then look at who needs A? When I have the data, who needs A? Here's your data. What's the benefit in that? You waste less bandwidth, right? Because you go to DRAM only once, not twice, for the same address. Sometimes we call this technique coalescing. Coalescing, basically you combine ongoing things so that instead of having to do two loads to the same address, you issue one load. It's like how many times when you're hungry and you're in the lab and your group is hungry, you send only one guy to the cafeteria to get the food for everyone else in the group. The same idea, right? Everyone is hungry here. They want to get the address A. You send one guy to DRAM, say, hey, get A for me, and then I'll distribute it to everyone else. All right. Now, because they're actually loading the same data, you don't have to issue multiple requests. Then let's say I have a store to A, store to B, right? Then I have a load to A. See how I have a store to A, which is a red data, a different data. The blue load to A has to go to DRAM because I have no previous store to A in the buffer. The load to A, can I get it from somewhere else? I have that in the store buffer. So I just forward the data over. Say, hey, here's your data, you're done. You don't have to go to DRAM, right? Then I have a load to B. Again, I can forward the data over. Now you guys got the idea, right? If you have this buffer, it will speed up your program. Yes.
Is there like any policy with the other?
Oh, go ahead. Great question. Basically, the buffer gets clear when you finish the write back. So when you have the request actually come back, you clear the buffer. Then you move on to write back. Once the data comes back, you clear the entry. Then you move on to through the pipeline. Because if you're in the pipeline, you can do data forwarding from the pipeline, so there's no need for them to be in the buffer. Now, let's say you finish the write back. Too bad, future load, go to DRAM. All right, because we cannot store everything indefinitely, we have limited buffer. And for the top two load, you're done, right? So this speeds things up because we can always do this forwarding. All right, there's many issues about advanced design. For example, I said it's a load 2A, but sometimes I don't know where I'm loading to. It's basically I'm loading the value that are in this register, which is dependent on another previous instruction. So I don't know the address I'm loading to. The question becomes, do you issue right now and guess? Which you can actually. Modern CPU actually do a lot of this guessing the address. If you're correct, yay. If you're not correct, throw it away. All right. Now, when you have the load store buffer, that's in the CPU. Can I do this almost the same technique, but for the cache? Yes. We call this the MSHR. This basically handle cache misses that are going to the same block because logically the same thing. You have a group project, one person, everyone is hungry. Why going to the cafeteria together except if you want to take a break, all right? But you send one guy to the cafeteria, buy the food for everyone. Hopefully you rush your project and you finish early, all right? Same logic here. You have cache misses from two different loads. Right? Two different addresses, but just happen to go to the same cache block. That can happen quite a lot, right? I have an array of integer. I keep processing them, so I have a lot of requests going to the same cache block. The thing is, well, if that's the case, it's not efficient to send 8 different requests to the same cache block because the DRAM would give you the same thing over 8 times with a lot of data. Bandwidth, basically. It wastes bandwidth, it wastes power, it wastes energy. Why are you doing that? Okay. So the idea is, well, we buffer them because we don't have to send multiple memory requests. So when I said the word memory requests, these are basically things that I send to DRAM. Here's the address, give me this data. All right. The better question is, well, how can I handle cache misses? Solution is this thing called Miss Status Handling Register, MSHR. It's always in your CPU. It's one of the structures not a lot of people talk about, but it's there to make sure caching works. Okay, so here's how it works. When you have a cache miss, I will put the miss related information, which basically includes this is the address I'm going to, and this is the processor that wants the data. Address A, processor 1, right? Because you have multiple processors on your CPU now. So now let's say processor 2 wants address A. What can you do? Combine them, right? You don't have to send another request. If you have a friend going to the cafeteria already, call them. Say, hey, I want food too. Buy it for me. All right, same idea. So you say now address A is demanded by both processor 1 and processor 2. Send one request and you're done. Processor 2, which come later, cut some time too. I don't have to send another request again. Another idea here is processor 1 has any future request to the same block. Combine them because it's the same block, right? Then we store who demands the data. And when you have the miss coming back, you know who to distribute the data back to. Now you basically hand out the data to processor 1 and processor 2, and here's your data. This allows you to eliminate redundant work. And one quick thing, because we have this buffer in a cache, right? So in some sense, this limits how many in-flight requests I can send to DRAM. If I'm running out of MSHR, it means that I wait until something is free before I send the request to DRAM. Okay. Now, any question before we start the majority of the rest of this class? All right. So here's the main topic, DRAM. The unit of DRAM is called a DIMM, by the way. It's not called 1 อัน or 1 แท่ง or 1 stick, right? It's called a DIMM. Dual inline memory module. It stands for dual inline memory module. The reason why that's the name of the unit is because it's called the memory module. Okay. So each DRAM DIMM is connected to the processor side through the memory controller. On your CPU, there'll be some area dedicated for this guy called memory controller, which send the signal. It coordinates with the load store buffer. Here are the requests I want to send. Memory controller take that, generate the request, send to DRAM. Get this address, get this address, get that address, write to this address, and more. All right. Inside the DRAM, how does it look like? Anyone buy one before for your computer? Anyone seen like the how DRAM looks? All right. Yeah, it's like a silicon with like black chip on top of it, right? And how about the fancy ones with like, yeah, those things. Why does it look different? Anyone know? Yeah, the shell. What's it for? Yes. Those things are actually heat sink. Basically, it allows you to kind of make DRAM faster, and hopefully you distribute the heat out better than like a DRAM without the shell, without the heat sink. So in the DRAM DIMM, it's broken down into smaller units. The first biggest unit is called the channel. So if you built your desktop before, you might have seen the motherboard where you plug the DRAM in. And they will have sometimes 2 colors. Those colors are actually the channel. And you can think of the channel as each individual pipes that you can stream data in and out. It's a physical wiring that are separate, right? So these are the channel. And for example, you build your computer, make sure your DRAM is spread out across all the channels that you have. Because if you don't do that, it's like when you have 2 pipes, but you drain the water only through 1 pipe. Why not using the other pipe, right? So you would use the both any channel available to your computer. The channels share the same clock. So if we go back to an earlier question, I think 3 weeks ago, we talked about the clock. Why does it have a different clock region? Because memory controller has the DRAM clock. So that's the guy that controls the DRAM, which use a different clock domain. When I say the word clock domain, it's basically this. You can have actually one global clock signal, but you can actually use multiple domain by using different logic to slow down the clock, essentially. All right. DIMM stand for dual inline memory module. We'll go into each of these subunit of DRAM in a bit. I want to go through like some figure first, so you see that in action. During each time interval, by the way, that means each clock cycle, DRAM can only transfer a limited amount of data in and out. Okay, in and out. That's the bandwidth. That's why some DRAM has higher bandwidth, because you can send more data in a unit of time. So because we use out of order processor, what it means is if I have 4 core processor, I can send many different data access to DRAM at the same time. Right? Because we don't stop on a load instruction anymore. We keep going. So it means that I have multiple data access to DRAM. Your program, by the way, now it's become software programming. Quick hint or quick guide on how to get performance. Make sure you try to exploit that as well. Be aware that your DRAM can handle parallel access and try to write parallel program that exploits the fact that you can issue a bunch of load to DRAM, if you will, right? There are a bunch of structure inside DRAM to allow parallel data processing. Well, I would say data retrieval, actually, not data processing, but it allows you to get 8 different addresses at the same time rather than handling one access. So this is a matter of, I don't get the speed, but I get to do a lot of requests at the same time. Right? This is different from a CPU design, which I give you a lot of speed. I can clock really fast. For DRAM, folks, here's your design trade-off. It's super hard to make DRAM fast. I cannot clock them really fast, so my solution, I'll give them a lot of data. If you request a lot of data at the same time, that's fine. I can do it to you. The GPU is a prime benefactor of that. The GPU do a lot of parallel access. And I can have a high bandwidth memory that can give you back like 50 or 100 addresses at the same time. All right, any questions so far? So we call this memory level parallelism. And you can design a program to have high memory level parallelism. Write a parallel program whenever you have to access a bunch of memory, make sure they can be serviced in parallel. And I'll talk into more detail on how you can do that. All right. If you know how the DRAM is structured, you can actually design your program that way. So here's how it's designed. The DRAM stick, quote unquote, that you buy, all right, you plug that into your motherboard. Basically, that connects to the CPU. All right. Usually, I think modern day motherboard has 2 channels, channel 0 and channel 1. If you have 2 DIMM, plug into both channels, exploit the physical connection that you have. Now let's zoom it in. You see that the front side and the back side, right? And you see the chip on both sides of them. Actually, it's 2 chips, not one single chip that pierces through the board. All right, it's actually 2 chips stick on top of it. The one of the sides called rank 0, the other side is rank 1. Why do we have 2 separate chips? This is one way for your DRAM to cheat on the clock. Usually, if you have a CPU, right? How big is one clock cycle? Is it number 1 or is it number 2? What's the clock cycle? One clock cycle. Well, theoretically, one clock cycle means you go back and come back. You go back and forth. So it has to be, the bottom line is what we call negative edge. The top line is what we call positive edge. So you have to go negative edge, positive, and back to negative edge again. That's one clock cycle, right? And when you clock in one cycle, you send one signal. Because that's what you can do, right? You can only send one signal. Now, how can I cheat this? I can have rank 0 use the positive edge, rank 1 use the negative edge, right? So that way, I can send data on both positive edge and another set of data on a negative edge, even though my clock. So the thing is, the clock is long enough for rank 0 to send the data over. So let's say rank 0 demand 1 gigahertz clock. If I do both edge, it means that my clock is too fast, right? Well, let me put it this way. Let's say this is 1 gigahertz. This whole thing. The period is the time it takes to do that whole cycle clock, right? It's equivalent to you have 1 gigahertz clock. If I have half the period, how fast is my clock now? 2 gigahertz. It just happened, my DRAM cannot support 2 gigahertz. Too fast. I cannot send the data ahead of time, right? So the way it cheats is I have rank 0 that start on a negative edge. send the data over, I wait one whole clock. But halfway through, when I have a positive edge, I cheat and I say, hey, rank 1, you go. So that way, both sides of the clock are doing something active. That's why we call this dual inline. That's why we call it DIM, dual inline memory module, because you send the data on both negative edge and positive edge of your clock. And because both ranks weight one for the 1 gigahertz clock, you're okay. Right? The next time I see negative edge again is already one gigahertz, for 1 nanosecond essentially. So that's long enough for me. ครับ
Going on to by the way.
Yeah.
It says 3200 megahertz. Is that actually
6 screen. That's actually 1.6. Yeah. You got the idea how they use that number. Well, yeah, yes. It does sound like a scam. But well, I mean, it behaves as if it works with like 3.2 gigahertz clock, right? That's how slow DRAM can be compared to the CPU. You can't clock that fast, right? So that's the rough idea on how this ranking work. That's why we have 2 sides, because we want to always cheat on this. The more we can cheat, the faster is your program. So why not? Just cheat it enough so that it doesn't break, or no one can hack steal your system or things like that. All right. Now let's zoom into the next step. The black thing, we call that DRAM chip. Okay. So the way DRAM chip is divided, for the purpose of this class, which is undergrad lecture, I'll just go to this detail, not more. It's divided into multiple banks. Think of this as like different actual banks that you can go in and take your money from. Right? Your money you have an account, that's your address. You go into the bank, you have an address, you can withdraw or transfer money to the bank. The reason why you have multiple banks is each address, similar to the cache set. What's about cache set? Every single address is mapped to a set, and only that set. All right, every single address will have its own cache set that you go to. Same thing here. Every single address has its own DRAM bank ID that you go to. So let's say you have address A going to bank 0. Right? And I have another request to address B to bank 3. Those are 2 different banks. I can go and get my data in bank 0 for address A, and at the same time, bank 3 operate and get the data from address B. So this is memory level parallelism. You send 2 address, you get the address you get the data hopefully almost at the same time. Both of them work in separately to get the data for you. So now that you know that your program is the address also has something to do with the bank ID. Should I write a program that go to only one bank, or should I write a program that tries to distribute my address to all the banks? You want to distribute your program to all the banks, to be honest, all the channels and all the banks. All right. Why? So let's say you have to send 16 requests. It's like when you go to macro and there's one checkout, that's like 8 checkout lines. When you go only to one bank, it's like everyone go to that checkout line. The other 7 don't use it. You wait a long time for sure, right? The distribution of your address will allow you to use all the checkout lines. So overall, your program should be faster. All right. Now that's one chip. Why do we have 8 chips? Go back one slide, see the picture. You have 8 of them. What's this for? Any taker? Any guess taker? More chips. You send 8 at once. More check off lane. Okay, all are great answer. The correct one is, though I would say the one that we are actually using right now is yours. I would make sure I still have 8 checkout lanes. All right. And it's just because the chips are smaller, each chip sends, in this case, let's say 8 bytes of data. How big is your cache block in the Intel CPU? 64. If I send out 8 bytes per chip, can I just use 8 chips then to set in one cycle the whole cache block? Right? So in one single cycle, once I have the data from the bank, this will be the first 8 bytes, right, of the cache block. So cache block would look like this, right? The first set comes from here, the second set of data comes from here, the third comes from here, the fourth comes from here, and the last one goes to there. And you have the whole cache block. One step, everything is ready. So basically that's how it looks like. Basically in your DRAM, it's still 8 chips. They would work together. That's why we named them rank. I would compare that to like when yes. Bytes. So your access from the CPU usually to the data word size, which is up to 8 bytes, right? But when you go to the cache, it operates in a cache block unit, which is 64 bytes. And we have a cache miss. That's when you interface with DRAM. So DRAM should give you back 64 bytes, not 8 bytes. Yeah, because there's no need to get just a part of the cache block because you want the whole cache block. Recall your cache simulator from Cisco. When you have a cache miss, you get the whole block, right? Same logic. That's why you need 8 chips because you want the whole block.
So like, you're using the whole RAM just to process one cache block, but I realized it's like 3,000 more cycles.
Yeah. So see how we can redesign basically how DRAM operate to make things faster, right? I think that's kind of like a example of architecture. Yes. Yes, you can basically send the first part in one cycle, then the second part in the next cycle. You basically have to spend more time stream the data out.
So each chip not full 64 bytes.
Well, you have a choice. You can also have a really, really high pin count, which is the actual wiring that comes out of your chip, but that costs a lot. For the DRAM manufacturer, that's actually a big part of the cost factor because no one wants to buy $1,000 DRAM.
It's 8 banks a little.
So that's like your typical CPU. Modern day DRAM that goes into a GPU, for example, look different now. It's actually because you have stacking, you have actually like metal, we call it through silicon via, which is the metal that stick through the whole thing. It's like when you have layers of like DRAM and you push like the metal stick through all of them. And because you have a 2D surface, you can put a bunch of these metal. Now you have way more bandwidth.
On DDR5.
DDR5 is more like this. But high bandwidth memory that's used in like A100 GPU will look more like the other one I explained that have DRAM on top of each other.
One bank can only give one bank.
One bank right now, with the default design, if you will, default design, you can get 8 bytes per cycle. That's like a maximum textbook kind of design. Obviously, you can redesign them. As far as I'm concerned, as far as my information have, I've paused this quite a bit. All right. All right. One chip had 8 banks. Yeah. one cache block, because one cache block is 64 bytes.
Yeah, each chip has 8 banks.
Yes. Oh yeah, you can then service 8 parallel cache blocks for bank 0, bank 1, bank 2, bank 3, bank 4, bank 5, and bank 6, and bank 7, sorry. And that's what we call one side a rank, because I would compare this to like when you see how the soldier march in like military exercise, we call those a rank as well, like a rank of units, right? And they'll, in theory, march together. That's why we use the word, because they would walk together. Hopefully no one like missed that for anything. All right. So DRAM channel, as I said, this is connected to the processor, right? The channel has their own data bus, which is used to transfer the data. The command bus, this is basically the command coming from the controller, which you go into the detail in the second half of this class today, all right? Basically, the command will be like read, write, and do something. Then the address bus. The address is like, that's the address you want the data from, all right? So when you have two channels, you have these separate bus. Okay, I guess I haven't really explained the word bus too much. When I talk about a bus, it's like physical connection that connects two ends. All right. The channel has its own control. Yes. Huh?
It connects to it. So it's just one wire from A to B.
Yes. You can connect like multiple guys together and read the signal. Because whatever the signal is on the wire, right? If you put voltmeter on that, everywhere you see the same value. So you can send the data to multiple places if you want to. So they have their own memory controller. So when you have two channels, you have two controllers. DRAM bank, as I said, basically they work together to stream your data in a cache block, right? And you have multiple rank to exploit the positive and negative edge. The bank works in parallel, give you memory level parallelism. In the bank, you have a shared command bus. So you can't send the command to all 8 banks at the same time. You need to send the command to bank 0, then bank 1, then bank 2. But the command I can send the command every cycle, which is really quick. Most of the time you spend the data inside the bank to try to get your data. So that's okay. You still get parallelism. You have to queue up the command a little bit, but those are the fast ones. The controller is responsible for sending out this command. All right. Let's take a maybe 10 minutes break before we now move along to the last topic today, which is the controller. I think we should be able to finish this whole thing in like 40 minutes before we then talk about some other cool technology that some of them is available now, some of them will hopefully in the next 5 years. Controller topic I really close to me. So we have this bank level parallelism, right? Which basically means that I can pick what request should go to DRAM. Basically, it means that my CPU can issue a lot of requests at the same time with out of order processing and a load store buffer. And my DRAM can handle a lot of requests, right? Now the job of the middleman is to figure out you guys go first, you guys go next, you guys go last. And how to make sure DRAM still operate, right? Inside DRAM, after you have all this bank, right? Internally, the problem is your capacitor, which store your data, is way too small to actually sense anything. You don't have enough electrons in the capacitor to sense that is that a 1 or is it a 0. Imagine you have a program right now playing some music, but it's not loud enough for you to hear. So what do you do? Turn up the volume, right? Through what? amplifier, you amplify the signal to make sure it's loud enough that you can hear what's the music. Same logic here. We can use the amplifier to amplify the signal to make sure I can now measure is that 0 voltage or maybe 1.5 volts. With that, I can measure is that 1 or is that 0. So if you guys are asking, why do we just store number in binary? Why don't we just store in one single capacitor? Why can't we store 0, 0, 0, 1, 1, 0, and 1, 1? And then between 0 volt and 1.5 volts, I have 4 different regions, right? It just turned out too hard to do that. We have a really hard time trying to figure out is that at the top part or bottom part. That's why we do binary. Okay. The thing is the charge has to be amplified. The amplifier is what we call the row buffer. We cannot amplify the whole DRAM at the same time. We can only amplify the subset of signal at once. Usually these days, the size of your row buffer is like 2 kilobytes, which is big. All right. A quick tidbit is like internally within DRAM, you need to subdivide this because these days it's so small that you need a local row buffer. It's like small amplifier to first amplify the signal close to the DRAM cell. Then you amplify it again in the global row buffer so that you can hear the noise. All right. And we use this to amplify the data so we can read the data. If we do not amplify, I cannot read the data. It's just impossible to read. And here are operations. Because we need to amplify things, right? So in terms of the status of the DRAM row buffer, I can have it open. It means that it is amplifying someone's data right now. That's the open row buffer. A closed row buffer is I'm not amplifying anyone's data right now. Okay, any questions so far? That's just a definition, open and closed. Open means someone's data is in the row buffer. Closed means no one's data is in the row buffer. To close a row, so let's say I have someone's data in the row buffer, all right? So this is your DRAM. This is a row buffer, right? Let's say right now, this row A is in the row buffer. And then suddenly I have another address. I have another address that say I want to read. Sorry, need to use a different color. I want to read from row B. What do you have to do? The first thing I have to do is put row A back to row A. Put row A data in the row buffer back to row A. Then switch in row B. All right. Now, if I have a read to a different row, I first need to close the row by writing whatever is in that row back to the original location, then open a different row. Okay. To read from a row, it has to be in the row buffer. Otherwise, you cannot read. All right. Agree on? All right. These are the rules. Okay. Now, to read the data, let's say I have an open row, has someone's data in there, and my read is to that row. The only thing I have to do is I just need to read them, and you're done. Because the data is already in the row buffer, so I just need to read them. If I need to read the data, but the row buffer has no one's data in them, the first thing I do is I would do an operation called activate. Activate means that I go and grab that row, amplify the signal, then I read from them. And then you're done. You can read from it. All right. Now, let's say I have an address to a different row and someone's data is in the row buffer. The first thing I have to do is called pre-charge. Pre-charge means that I put the data in the row buffer back to the original location. That's pre-charge. Then I activate a different row, put the data in a different row into the row buffer. Huh? Yeah. So let's say I have DRAM here. And this is my row buffer, right? Right now, let's say row A is here, but I want to read row B. The first thing I do is put A back to the DRAM. So A put back here. Then the next step is I put the row B into the row buffer. Then the third step is I read from it, right? This is pre-charge, yeah. This is called, the second step is activate. The third step is read. Now, does it explain whenever I said if you have a cache miss, the time it takes to go to DRAM vary from 50 to 100 nanoseconds, depending on do you have the data in the row buffer or not. If it is something like 30 to 40 nanosecond cycle right now.
That a lot. That time scale a lot for.
Yeah, what to do?
RAM.
A lot for what?
The complex DRAM. That a lot of time.
Yes.
Because we're talking in nanoseconds. So that's pretty
Well,
fast.
let's put it this way. From 1x, which is hit in the row buffer, I have the data in the row buffer 1x. If I have to activate 2x the time. If I have to pre-charge and activate, usually 3x the amount of time. Yes. But I mean, the row is 2 kilobytes. So you're going to end up doing the worst case scenario quite a lot, right? The quick note is there's also like additional timing for some. If you switch from reading to writing, you have to wait some time. If you switch back from writing to reading, you have to wait some time. There are like a few more things when you send the data over from the bank. Let's say the data is ready, right? To send the data over, you also have to wait because the data bus is being used right now. So basic operation, read and write command is called the time it takes is called tcache or trcd, row to column. If you go and read DRAM specification with this, now you know how fast is your DRAM. They will actually say tcache is this many nanoseconds, trcd is this many nanoseconds. The pre-charge time is TRP, row pre-charge. RP is coming from row pre-charge. This allows you to prepare the row buffer for the next row of data. And the activate is RAS, row access strobe. Strobe means I just want to get to the row and activate them and actually put them in the row buffer. Yes. Oh, column access strobe. Row to column. RCD, huh? No, not store. Column access strobe. Yeah. P. STROBE. Strobe. Yeah.
What's a stroke?
What's a stroke? Yeah.
Random.
I need to ask circuit guy. Actually, let me look it up. To be honest, that's a nice question.
What RCD?
RCD row to column. I forgot what the D is. Sorry. RP is row pre-charge. IS is row access strobe. The thing is, when you put in a row, each data is, we call this a column of data. That's why reading is go to the column and read that. Column access. Huh? Row pre-charge. Row pre-charge. Row access strobe. I'm not going to ask you what they stand for. The reason I put it in is because when you read the DRAM specification, you can look and they'll have the number. And now you know how fast is the DRAM that you're buying. Yes. Oh, the delay. Okay. Row to column delay. Okay. So that's basically when you have a row ready and you need to read the column, which is that hash block, what's the delay that you have to wait until you read from them. You can read from them.
So when we read the specs of we are expecting like lower, better.
Well, you know that this is now to know how fast is the DRAM. That's it, right? You know how bank works. That's like the lowest level from the programming point of view, right? So you kind of know roughly now that each memory access is going to take this many nanoseconds, which you then multiply to number of cycle, which means that you know how costly is your memory access. Lower level than that, you're basically designing DRAM, which is a different job, right? I'm talking as like from the perspective of the software programmer. If you need to buy DRAM or you need to figure out like where's my bank ID, right? Now you can read the specification and now you know this part of the address, this bit is the bank ID, this bit is the column ID. Yes.
But do different type of RAM have like that amount of the different things. This depends on the chip.
Yeah, this depends on the generation of the RAM.
Doesn't the chip it comes from the same pack anyway? Like, mostly Samsung or like
A micron, like yeah.
so won't that be the same throughout like the slot?
They usually they'll differ by like between 3 to 4 nanoseconds, which is quite a bit. Huh?
Does that really affect stuff?
Yes and no. So if you buy like 24 DDR3 2400 and DDR5, which is way faster for this timing, you're gonna see the difference. So each generation you lower the timing quite a lot, and then the older one from the same generation is not gonna be as fast as the newer ones. But the thing is, when you buy DRAM, the first thing you look is what's the capacity. How many people look into the timing? But when you do, you can see the difference in the price, right? Because it does affect the time. How many times you actually have to access your array? When you run a program, you access DRAM a lot, right? So that if you are the guy that say 3.3 gigahertz CPU is not as good as 3.6 gigahertz GPU, these things matter. All right. So the normal sequence is you can pre-charge, activate, and read-write. Note that because pre-charge is essentially closing the row, you don't have to always wait at the last moment to close the row. You can close it right away if you know there's no more DRAM access to that row. You can say, hey, I'm going to proactively pre-charge things to make sure row is closed for the new row to come in. There are also things like when I switch from read to write, is write to read latency. Write to pre-charge is write to pre-charge latency as well. There's also bus latency to transfer the data across DRAM to the CPU. And now here's an operation. I'm basically stealing my friend's every single semester. So this is on my friend's paper. HPCSA is one of the top conference in architecture. And he has a really, really nice background paper that explains how DRAM operates. All right. There are two things I want you to look into for now. Each bit in DRAM, they will have the cell capacitor. The cell capacitor that I highlight, is it blue? You see blue, right? So that's where you store the data. Okay. If it's greater than half, that's the number 1. If it's lower than half, that's the bit 0. So it's bit 1 or bit 0. Those are too small to measure. I cannot measure is it greater than half or lower than half. Okay, that's the first thing I want you to notice. Second thing, every row share this bit line. The bit line, imagine the wiring that goes through all the row. And you have one much bigger capacitor, we call the bit line capacitor. Think of it as that's the pool of a much bigger capacitor that I can measure and put electrons in. Okay? With me so far? No. All right, when you store a bit, 1 bit in your DRAM, you need the cell capacitor that store your bit. Okay? Each row has this shared bit line capacitor that store a bigger pool for electrons to flow in. Okay. Now we will use the bit line capacitor as the reference. Is that a 1 or is that a 0? So if I am not reading anything, bit line capacitor should be at exactly 1/2. 1/2. All right. The first step when you want to read something, you see the switch on the diagram, the two switch. The first thing is I close the top switch. What does that do? We call this step charge sharing. It means that my cell capacitor and the bit line capacitor share the charge. They will go to the same voltage, essentially. They'll converge to the same voltage. All right, so now my next question is, bit line capacitor is exactly 1/2. If my cell capacitor is greater than 1/2, what's the voltage on both capacitors right now? If one of them is 1/2, the other one is more than 1/2, I add them together. Is it bigger than 1/2 or lower than 1/2? Bigger than 1/2. All right. So let's say the cell capacitor store the value 1. When I close the switch, I'll get better, not better, greater than 1/2. Okay. The next step is I kick in the amplifier. I start to kick in the sense amplifier by closing the switch at the bottom. When I close the switch at the bottom, I connect the whole circuit. And the job of the amplifier is this. If I see greater than 1/2, I put electrons everywhere. If I see less than 1/2, I drain the electron from everywhere. So in this case, it's greater than 1/2. The next thing that happened, every single capacitor will start seeing more electrons flowing in. With me so far? Somewhat. Somewhat.
So that amplifier just you make it so it's more clear for the system.
Yes. And also make sure all the capacitor now have, if it's more than 1/2, it's filled up. If it's greater than lower than 1/2, it drain everything. Everyone is connected to this circuit. Yeah, because wire works that way. If I have a wire, I have the same voltage. I like how okay, I school circuit. All right, so you see, after the sense amplification, right? I can read. That's when I can read. Now, once I finish reading, right, I have things in the row buffer. The next step is I have to pre-charge. Pre-charge basically means this. I have a really filled up in the tank, in the bit line capacitor. It's filled up. Like look at figure part 4. It's filled up. I need to make it 1/2 again. How do I do that? I disconnect everything and wait until it drains to 1/2. So see how from here I connect everything. I now disconnect everything. That whole circuit will have a reference voltage, which means that I will supply the power so that it always go back to this value. That value is 1/2. So the bit line capacitor will always go back to 1/2. That is when you finish pre-charging, because then you can go to a different row, which has a different capacitor, and close them so they share the charge again and can read the next row. All right. Too fast, kind of. Okay. Notice how this thing is gone. So I have this status again. Exactly half, so I can read the next cell. Yes. Uh-huh.
Oh, so like split to one.
Yeah, you're done.
Slowly die down, slowly die down.
Yes. Yes, it will slowly die down because capacitor will leak electrons.
So what if you want to do?
Let's say you store a 1. If it slowly dies down, eventually that becomes a 0,
Yeah.
which is a bad thing. So every single computer has this thing called refresh operation. At this point, every 64 milliseconds, every single capacitor is rewritten to the initial value, either top 1 or 0.
So if I want a 0, I have to wait 4 milliseconds. Sorry, that's not.
No, you can write to it. You can definitely write to it. Oh, okay. So when you write to this during charge sharing, right? During charge sharing, the amplifier would basically rewrite the signal. So there'll be electron flowing in from the amplifier. Say, hey, that's a new value. So if you go from 1 to 0, you drain everything. If you go from 0 to 1, you put everything back. Yeah, it's different. Oh, yeah, yeah. Basically, we put the reference voltage to be exactly half of the maximum. And because we have a reference voltage, electron will flow out of the capacitor until it hit the same voltage, the same stuff,พลังงาน stuff, you know.
The half of
VDD. Yes.
So how can it?
Oh, you have the input reference voltage coming from your computer. That's actually when you power it on, there'll be some logic to make sure that's the supply line that go in. That's exactly how. Yes. You can do read write the same thing. Write is basically sense amplifier at the bottom, control what's the value.
So okay, I'll still talk about the last one.
Uh-huh.
So that is like the state where it resets.
Yeah.
Because this is the first state. So if I want a 0,
Uh-huh.
how will I make it a 0? But when you start carrying the cell capacity is still full. And then when it shares voltage will be over 1.5, and then the amplifier will.
Okay, got it. So in the case of the write, you don't amplify the signal inside DRAM. You amplify by draining and rewrite the signal that comes from the external source, which is the data you want to write it to.
We use the external constant voltage.
Yes, that's the data pins that go to inside the DRAM. That like when you have the DRAM operation, right? That's a shared data bus. So in the case of the write, the shared data bus will be the data you want to write to. They'll have the correct value. The sense amp would basically amplify these guys into DRAM instead of reading something from here outside into the data bus.
So this is just reading from somewhere.
Yeah.
Just copying.
Yeah. All right. So quick recap. This also means that if I have a program that goes to the row buffer a lot, they can be faster than a program that go into all different row buffers. All right. We call this row buffer locality. Access to the same open row is faster. All right. Access to a different row is slower. More of the time, to be honest, when you write a program, this is a part that's a little bit too low level. You don't have to consider these things. These are handled by the controller. The controller would try to group requests to the same row together. Okay. That's the job of the controller. We try to maximize whatever we have right now. These are the ongoing requests that I have to schedule to DRAM, and I use that information to send the same the sequence of requests to DRAM in a way that I get as much bandwidth as possible. Memory scheduler is responsible for maximizing sending requests to all the banks. Then for each of the individual banks, send them to the same row as much as possible. And more make sure DRAMs do operate. Don't clock too fast, don't clock too slow, refresh every 64 milliseconds so you don't lose data. And here's a quick overview of the test. You're not allowing anyone to use that bank. There are ideas actually that many of I told you like my research group, the research group I'm from at CMU work on DRAM, right? So we actually have a lot of papers on DRAM refresh and how to reduce that overhead. Because imagine when you have DRAM that's like 64 gigabytes, for example, you spend 4x time more refreshing, right? So this is gonna get worse and worse. So there are works that looks into how to make it cheaper so that when you buy a big DRAM, you don't feel that effect. But in theory, when you refresh a bank, you turn off that thing. No one can access it in the meantime, and then I can enable it when I'm done refreshing. Now, some of the basic idea that your computer is using right now is they don't do the whole bank at once. They would spread them around and try to be smart about it. For example, if no one is using the memory right now, I'll sneakily refresh things, right? Also, if you, for example, just access that row, you realize that your charge is now full, right? You don't have to refresh the row for another 64 milliseconds. So that's another idea. Now, if you look at a controller, these are, let's say now you have 4 processors. Each processor has its own program running, right? And they will have data access because that's your program. You access data, right? So you have the yellow request, blue request, the red and the green request coming from all these processors. The job of the scheduler is to pick which one to send to DRAM in order to make sure all these 4 programs are fast. All right. I just pick the order in a way that I maximize bank level problems, send all to different banks, or I will send them to the same row. Hopefully I group it that way, right? Otherwise, otherwise my performance would drop. Otherwise my performance can drop. So quick thing about scaling 101, right? I have to make sure I don't do it faster, for example, than the TRP, the time I need to pre-charge, right? But the basic goal is, if I have a bunch of requests, I want to maximize requests to the same row, because that's fast. Want to send all the requests to all the bank, because that's fast. And make sure, let's say I have 4 programs running, I make sure that they all get the fair share of DRAM. Because let's say I have 4 programs, the first program is really, really, really friendly toward row buffer. I can have a policy that prefers any program that use the same row, and the other 3 programs will never get the light of day to use DRAM. Right? So I have to make sure they're also fair. They have to be fair. And then I have to make sure the timing is satisfied. Don't clock too fast. Don't send the command too fast. Okay. One policy you can do first come, first serve. Something we learned a long time ago, right? Which kind of, it's actually okay. Because the oldest request is likely the most important. Okay, so I want to service them quickly. Now, can we do better than that? Huh? Can we do better than first come, first serve? So why don't I have a policy called first row hit, first come, first serve? It's like basically the same as first come, first serve, but if I happen to have any request going to the same open row right now, I send that guy first. So basically, we call this FRFCFS, which is kind of like the default policy for your memory scheduler in your computer is highest priority, row hit. Then first come, first serve. Okay. Any questions so far? All right. Now, before we go into a little bit more example, which I think we don't have time for that, we might have to do it next week on Tuesday about like, let's say I have a bunch of requests coming and here I can ask you how long does it take to process this thing? The next thing is memory mapping because you have multiple banks, right? And I said each address will map to a certain bank. It also means that you have to pick what address is your bank bits. Similar to the set ID bit, but the index bit work the same way. It's a design choice. Now you can actually pick what bits is your bank bits. The question is, where will be the channel bit, the rank bit, and the bank bits? Because there has to be a systematic way to put them so that you get better performance, right? If you put it at, for example, highest address, the highest part of your address is likely to be a bunch of zero. So then all your requests will go to bank 0. Probably not a good idea, right? Maybe you want to put it lower. If it's too low, it will coincide with the set ID. That's way too low because you go to the set ID already, you hit in the cache, right? We call this part memory mapping. And there are multiple strategies because the OS actually does have control over when I have malloc what bank am I going to? The bank bit is high enough, is actually high enough that you have some control over what bank you want to make the request go to. Also the channel bits. All right. I think we have enough time. So one thing I can do is for every next cache block, right? I can send the next cache block to the next bank so that then I have a for loop that go through my array. The first batch go to the same cache block, bank 0. Then the next cache block go to bank 1. What's the benefit into that? Both of them will get processed in parallel, right? If you have a for loop that goes through your array, the first block is bank 0, the second block bank 1, the third block bank 2, the fourth block bank 3. It basically means that you are one cache miss. A process together for the whole 8 cache blocks from bank 0 to bank 7, right? So we can put the bank bits right after what? Somewhere in the tag bits. If I go through all the sets, right? Before I have the cache trashing, basically that's going to the other bank because I can process them quickly. So we can do cache block interleaving. Cache block interleaving will allow the consecutive cache block access across the different address space from your program to go to different banks. The benefit, as I said, is when you have the for loop that go through your array, they now are processed in parallel in DRAM. You get a really high memory level parallelism for most typical program, to be honest, right? Because that's how you process your array. Row interleaving means that instead of sending them to different banks, I send them to the same row. So I will put the row bit and bank bit in such a way that consecutive access are mapped to the same bank, but the same row. So consecutive cache miss will be processed sequentially, but really fast. So that way, right, you lower the amount of time to get each cache block. Then you would spare the other bank for another application, for example, that runs on your CPU. Or the same application, but a different data region that go to the same, to different bank. Now, this is the part I kind of want to go over next week, which is when you call malloc, what happened. This is not related to memory mapping. It's not related to memory scheduling. All right, so next week we'll start to talk about the memory scaling policy called first row hit, first come, first serve, with some examples from the last semester exam. Which, to be honest, everyone kind of flunked that question, so I want to go through an example to kind of show you how it's done. All right. Then we'll go through the example of when you call malloc, what happened. On Thursday, I'll talk about like random topics on architecture and network and system. Then Friday, exam begins. All right. Friday, exam begins. Same deal. I'll be online on Discord. And here in this room, I got the room between 9 o'clock to 1 o'clock. In this room here, if you want to drop by, say hi. If you want to stay home, just join Discord. All right, because it doesn't make sense if you have no class on Friday. Why are you driving? All right. So, any questions before we adjourn? I just realized I go way too fast. Since we have 10 minutes, should we talk about the refresh issue? So when you buy DRAM this day, right? Let's say you have a server that you have to make sure it's online all the time. I cannot afford to have a blue screen, all right? That crash everyone's program. If I do have blue screen, I better have another server backing things up, right? But one of the common things that we do is for the DRAM that goes into the server, we use a special DRAM called error correcting code DRAM that kind of have a mechanism to basically correct any bit flips from 1 to 0. ECC DRAM. That's why they are more expensive. You see more chips on it. Basically, they have more data that embed, like this row should have these bits. If it's wrong, correct it. There are some method to figure out how to correct that. These are things that can go wrong within the DRAM cell, right? Capacitor lose charge over time. We do have to refresh. You're gonna faults. Electrons go out of the cell by some random natural occurrence. Actually, like random gamma particles hitting your electrons. It's gone. Literally, really. It actually bounce your electron off, right? Then you have blue screen. How many people hate that? Yeah, we all hate it. I was playing games and blue screen, like lose my progress, right? So these are faults. We call this faults. Over here, for example, you can see that same diagram, right? Originally it's full, right? And at some point, somehow it's less than full. And as I said earlier in this class, you have to periodically, every 64 milliseconds, refresh the whole thing, okay? Because you have charge leakage. And we call this operation refresh. On the spec sheet, there's a TREFI that determines the frequency of how often you have to refresh based on the DRAM technology. Okay. You also can have error. We can try to detect it and correct it because this ECC DRAM. And I think that's kind of the wrap of what I want to talk about today. Most of the time, well, for the correct error correction problem, right? Just ECC DRAM. Yeah, most of the, I think current technology can correct up to 5 bits, which is really rare that you have 5-bit error within a short amount of time. Most of the time you have 1 or 2 bits, then you correct itself, so it never go beyond the 3 or 4. 5 is like extreme. Yes. It can operate as fast as normal DRAM. Basically, the way they do it is they put more chips in, and those chips is used to encode your data, and it would tell that encoding will tell you exactly is there any error, and if there's an error, what bit flips. Yes.
What's usually the price?
I haven't checked for a long time, actually, for a few years. Actually, can someone search like ECC DRAM with the same spec?
I'm pretty sure DDR3 is pretty cheap now. You can buy like 128 for like 5,000.
Yeah, I think, but no, it's gonna be hard to buy a motherboard for the 3.
Yeah, this is like a server where
Yeah.
that is a host to get it.
Yeah,
Oh, but 7,000 for 60.
it's not bad. Per gigabyte, it's not bad.
Why isn't it like standard?
Why isn't it the standard? Well, I mean, these days, how often you actually run into blue screen or bit flip? So because you can also use software technique to try to detect and kill the program, right?
Server only happen.
Yes, because in that, well, in most cases, server, you're basically, you want them online 24/7, right? And when you have your computer online 24/7, they're more likely to do weird things. Imagine how many bugs that can come up in your software, right, in like 3 days. If you run it for 3 days. Yes.
What's for like SSD? What would they like?
Great question. So SSD have this thing called a RAID technology, RAID. They use redundancy, basically additional hard drive to back things up. And they have a systematic way to correct the error. Some version cannot correct, but it will tell you change this drive because this thing died. Then you switch that drive out, put the new one in without you having to power thing off. Yeah.
Another company I was like rate video or like video for hard drive rate, all the rate. I can't remember the